I'm a maths first year at Mansfield College.
Brilliant. Nice to have you on the stream, of course. In chat today, I'm joined by Lauren and Max. Lauren, you might remember from Probability a couple of weeks ago. Max is joining us. Max has been helping out on online events, I think, since the first lockdown started last March. So you might have met Max on an event before as well. Let me just check how chat is going. As always, we're running chat underneath. This is in slido.com/OOMC if you want to join in. I think I've set everything up to be unmuted and broadcasting live. So let's get started. Let's start by talking about what's coming up today. Coming up, we've got, I thought I'd start by showing you the solution to that one Pigeonhole Principle question that we didn't do last week, that I left as homework. I don't think I've shown Deepak this question. Do you know what this question is?
No, I don't.
Oh, it's going to be a surprise for you. Okay, right. We're going to do a Pigeonhole Principle question that Deepak hasn't seen. And then our kind of main course today is a section called Fantastic Graphs and Where to Find Them. We're going to do some curve sketching. Brilliant. Cool. As I said, in chat, Lauren and Max. Right, okay. So I need to switch over to here and switch this over on here. It's a complicated setup that's not getting any simpler the more I do. Right, okay. Brilliant stuff. And I'm going to say hi to a few people in the chat as well. Hi to Lily and Raphael and Silu and Athena and Anonymous. You can be anonymous in the Slido. You don't have to have a name. You can set your name to anything you like. So watch out a bit. If you see someone with a famous name, it might be a famous person or it might not. Right. Which has given us a lot of fun. I've realised I haven't plugged everything in right at the start. So I'm going to start by saying, Deepak, do you know what the Pigeonhole Principle says?
Oh, it's like if there's n boxes and then there's n+1 objects in those boxes, there's at least one box with more than one pigeon in the box, something like that.
Fantastic, yeah, great statement off the cuff. So yeah, if you've got more pigeons than pigeonholes, and you put all the pigeons in the pigeonholes, doesn't matter how you do it, you've got a pigeonhole with 2 or more pigeons in. And in fact, there's a generalized version we talked about last week, which says if you've got lots and lots of pigeons, more than k times n, the number of pigeons, then there's at least one pigeonhole with at least k+1 pigeons in. Good, right, okay, here we go. So the question that we didn't answer, we did a few last week. If you're interested and you weren't with us last week, then the video's on this YouTube channel for you to catch up with over there to see what we were doing last week. And YouTube's giving me an error message, and Daniel's asking me about a drawing tablet. What's the priority here? YouTube says that our smooth streaming it's not smooth, so we've got jerky video today. It's probably because I'm running a lot of stuff. Right, okay, waffling around. Daniel, I'm using the cheapest graphics tablet that was on Amazon at the time that I bought a graphics tablet off Amazon. With obvious consequences. Okay. Here was the question that we didn't do last week. Works like this. There's a square of side length 2. Oh, dearie me. Side length 2. And we put 9 points into this square. And the question is there a triangle of size, is there a triangle of size 1/2 or less? Or is there a combination where, is there a configuration where that triangle doesn't exist? Can we put 9 points in without getting a triangle of area 1/2 or less? Let's put that target up. A triangle with area, oh dear. Ha ha ha. Triangle, there we go, that's spell. Area 1/2 or less. And I think Christian phrased this as a question, does this have to exist or not? Cool. Smooth enough, not now actually, sad face, says Athena in chat. So that's what happened there. Right, cool. I think opening the whiteboard might have ruined everything. Cool. Keep freezing. Yeah, okay, let's reconsider how we're doing this. I'm going to close some programs. Bear with me 20 seconds, everyone, as I try and close some things to speed stuff up. My computer's overheating from doing too many things at once. Do I need all of these things open? I'm going to sacrifice this one. We're going to just keep that and that and that because I need that for driving this and that one. Right, good. Okay, that might be slightly better. We had this problem a lot in the Matt live stream last year, that the more ambitious I get with the live stream, the more stuff I try and do, the more we break the live stream and my computer overheats. Sorry, computer. Right. Okay, so we're putting 9 points inside here. Is there a triangle with area 1/2 or less? Deepak, you've seen this question for the first time about 2 minutes ago. You got any ideas on how to get started, or ways that we might like to think about this problem?
The only thing that really springs to mind is trying to find 9 points that are sort of as far as possible. And then an arrangement that comes to mind is sort of like the numbers on the telephone, like the 1, 2, 3, 4, 5, 6, 7, 8, 9.
Yeah, okay. So if you space them out, you mean like spacing them out as much as possible, right? Yeah, okay. So if you space them out this much, to put them in the middle of the sides and the middle, like a telephone, for real, then I think the smallest triangle you get, the smallest triangle you get has side lengths 1, 1, root 2, and it has area 1/2. So even in this case, with the things spaced out quite a bit, there's a triangle of area 1/2 or less. People say the live stream might have got slightly better as a result, possibly. Maybe not. Okay, K-pop fan says it's a bit better now. Good, right. Teething trouble. So this is quite nice. This shows that in this sense, if you put the points in like this, then you still get a triangle of area 1/2. This gives an indication that maybe 1/2 is the kind of magic. Even if you space the points out, you get a triangle of size 1/2. We could do slightly better than that though. We can in fact prove with the pigeonhole principle that this is kind of true no matter where we put the 9 points. I think people in chat are helping you out. And I'm going to go to... If you want to say anything pigeonhole principle wise, or do you want me to say it? Or?
I don't really know. I wasn't too familiar with it, to be honest. But...
So splitting into eighths, Lily has just said in chat, splitting into eighths is a good question, good idea, because then you've got 9 points, so you've definitely got 2 that are in the same eighth. So you could look at your eighths and say, aha, I know I've got 2 in one of these boxes. Actually, that sort of doesn't help you very much for the area of a triangle, because you kind of don't know where the other corner of the triangle is. And there's anonymous people in chat telling me, if you split the square into quarters, then you get something slightly better. So if you split the square into quarters like this, each of these has got side length 1, then there must be, no matter where you put the points, there must be 3 points in a box, one of these boxes. Maybe it's this one. Doesn't matter which. Yeah, here we go. And then the 3 points inside here, let's say, well, the biggest triangle that they could possibly make has height 1, kind of height more than 1, and width along the kind of perpendicular width here, at most 1. I guess the biggest triangle you can make in this square uses all of the height and all of the width, something like this. And even if you make a big triangle like that, then its size is 1/2. So that's the kind of pigeonhole principle approach to this, to say, aha, if I split it into 4, then I can force 3 points to be in the same quarter. Yes. Ooh, and yeah, so I had a lot of chats with people. Lots of people wrote into me with suggestions on how to do this problem. By emailing oomc@maths.ox.ac.uk. Got to plug it, right? I had a lot of conversations with people with other ways of splitting up the square, which this anonymous person has just reminded me of. People wanted to split the squares up into different ways to try and prove different bounds on the size of the triangles, which was very interesting. Okay, right. The thing I like about the pigeonhole principle doing things like this is that you don't actually have to really think about where the points are. You don't have to do this kind of tricky thinking about what shapes you make as you put the points in, and what the network of spaces of shapes looks like as you go through. Cool. Right. Okay. That is the Pigeonhole Principle question from last time. I saw a request in chat as well to talk about the shortest distance problem that I put in the further reading, which I haven't prepared stuff for, but we might come back to in a future episode. And someone says, what's the Pigeonhole Principle? We've got a 1 hour video for you. You're going to love it. If you go to this channel, and you find the most recent live stream, episode 4 that we put out last week, was all about the Pigeonhole Principle and problems. This was a leftover bit from last week. Right, okay. I've stolen loads of Deepak's time to talk about a problem that I didn't even tell you about. It's very rude of me. Let's do fantastic graphs and where to find them. Do you want to do an introduction or just get going?
Yeah, so what I've basically just done is I had a little look online and I've gathered together some of my favourite graphs of all time, including my very favourite graph of all time. I'm very excited to sketch. And what we're going to do is some of them have some interesting applications that you probably wouldn't think actually exist when you're just in the middle of just sketching them. So what we're going to do is have a go at sketching them, and I'm going to talk a little bit about where you might find these. So should we go to our list of graphs?
Brilliant. Yeah, shall I grab one in?
Yeah.
I'll pull one in. Do you want this one? Or yeah, I'm going to
yeah, sure.
Let's put this one in. Okay, this is the first one. We've got a kind of set list down the right. So this is the first one we picked. Y equals x times sine of 1 over x. Let's try and sketch it.
This graph, all right. This one isn't too particularly related to any other fields. Good, we're going to start it off slow. We're not going to bombard you with too much excitement, but we're just going to have a go at sketching this. And now the first thing you should really do before your pen even touches the paper is you should be thinking about the function and what's actually going on. And already you can see things are going to be getting a little bit messy because already you have a 1 over x here, which begs the question: what happens at x equals 0? Because as you know, dividing by 0 is illegal, mate. You can't do it.
I love that.
Also, you've got this.
Sorry, I love that as soon as you saw a 1 over x, the thing you're not allowed to do is divide by 0. So obviously that's the first thing you want to try. The only thing that's banned. Sorry, carry on.
So we already have this, what happens x equals 0. And then we should also think about what's really happening with this x. So a couple of things to remember. Sine is always between 0 and 1. I can't think of a picture for that. And x is going to be getting a bit bigger. So what my advice would be, firstly, anytime you have a graph that's x multiplied by something, especially if it's like oscillating like this, if you've got any x's, any sines, wait, I have to make sure I'm drawing in frame here.
Oh, are you drawing somewhere else?
So what I'm going to do is I'm going to draw out the lines. Y equals x. Oh, that's terrible. And the reason I'm doing this is this function here, because sine 1 over x is going to bounce between -1 and 1. So this is going to end up bouncing between x and minus x. So we're going to have behavior where it's hitting some points here and some points here as it's going on, as it oscillates. This is just some general intuition about how the graph's really going to look. And now what we should really be thinking is what happens when x is either big or when x is small. We'll consider x as big first. X is small is a little bit interesting. So when x is really big, well, x is just going to get really big. Fair enough. But 1 over x is going to tend all the way to 0. So now you've got a bit of a x which is just getting bigger and bigger, multiplied by something that's approaching 0. Now this is the $1 million question. It really is. This is why graph sketching is such an interesting exercise. Like, this is why they get you to do it in interviews, because a lot of the times there'll be something behind the scenes where they want you to sort of work it out. So this one, has anyone got any ideas what might happen as x gets really big? The $1 million question.
So people are there's a little bit of a delay, and people are still talking about 0. People have got some great suggestions for 0. An anonymous person says that it's oscillating, which is true. That the sign's going to go between 1 and -1. So this thing's going to go between x and minus x, I think, between those dotted lines. Let's see if we can get someone to comment about infinity as well. I'm going to risk joining in with the chat at the same time, at the risk of melting my function. Melting my function, melting my computer.
It's a good debate about x equals 0. Okay. Approximate sine x. Right, I think the chat might take too long to catch up.
Oh, they're getting there. They're getting there.
We're gonna have to just ditch target audience, like audience participation. Well, so the idea is that what 1 over x times by x, so yeah, it does tend to 1, but the reason why is we're gonna have to be a bit engineering here. We're gonna have to say what 1 over x. What we can do is find a Taylor expansion, and if you don't know what a Taylor expansion is, it's sort of oh wait, hang on, I'll make sure I'm getting this right. Because that's like x equals 0 in it. I'm just thinking, because I'm always trying to introduce things that I don't think they'll know.
yeah, it's fine. I think so. When 1 over x is a really small thing, I think we've talked before on the live stream about approximations. We've talked about a little bit about having like an approximation to sine. You can think about an approximation to sine when the number inside is very small. It turns out that if you're using radians, then an approximation for sine of thing when the thing is very small, that sine of thing is pretty close to just being thing. I'm going to put that on the board just so that it's written up in maths. Here we go. I'm going to use A. I'm going to use A. If A is small, then sine of A is approximately A. Okay, that's a fact that I learnt at some point in A level. I can't really remember when. So maybe people have seen it before, or maybe not. And I guess Deepak's using that to say, well, here, when 1 over x is really small, I can approximate this bit, sine of 1 over x, by just 1 over x. Brilliant, okay. In which case, x times 1 over x is going to be like 1. It's kind of amazing. This thing behaves a bit like the number 1 when x is really large. Cool.
Yeah, it's interesting because this sine term is essentially sort of cancelling out with the x as it gets really big and it eventually approaches 1. So what might just be useful is putting in this line x equals 1. Oh, let's draw a bit higher. Y equals 1. All right, now, so we know what happens when x gets really big. Now, when x gets really small, I saw quite a bit of debate here. Now, we should really be thinking, if we look at the function 1 over x here, it looks something a little bit like that. So when x gets to 0, or as it tends to 0, it starts getting really, really high. So sine 1 over x is going to basically become sine of something, but increasing more and more and more. And what that's going to look like is something oscillating. The sort of, if you're going to think of it in like physicsy terms, the sort of frequency of the oscillations is going to be gradually getting higher and higher and higher. And then as it goes towards 0, you're basically not going to... It's just going to become a mess.
I love that frequency plot. I'm going to zoom in on that frequency plot. Sorry, you make it. Whoa! This is a pretty good sketch. Yeah, okay. So we got this thing with increasing frequency as we come in towards 0. This is about to get engineering, says someone in chat. I think it's time we try to. I think it's time we try to join the dots and put a sketch together of what x sine 1 over x looks like.
So already, the thing we're going to make sure is that the roots. So not the roots. So as it goes further on, it's going to be oscillating slower and slower. So the roots are going to start getting more spread out.
Yeah.
And then as it gets towards this 1, it's going to have sort of behavior that looks a little bit like that.
Oh wow.
And then it's going to go through here. It's going to hit the bottom, and as you can see, the waveforms are sort of getting smaller. Remembering that it's bounded above and below by x until the frequency gets sort of too much that you can't really see.
Oh wow.
Some of that.
Okay. I like that you've pieced together lots of different. There's lots of different parts to this. That sine 1 over x is pretty weird. Sine 1 over x has this kind of increasing frequency as you go in. And multiplying things by x somehow has made this even weirder. That it's behaving really strangely as it goes in. Yeah, maths, engineering, snobbery, applied maths. I will cry. This is why I'm not allowed to talk about my research on the stream. Right? Yeah, okay. I love this function. Look at this. It's got so much going on, right? It's quite compact in the way it's written down. But there's a lot of strange things going on in here. Oh, wow. I know the audience a bit, I think, and I reckon some of them have put this into Desmos. Maybe as soon as they saw it. So some of them, let's say, they've been polite in not mentioning Desmos yet. But if you put this into Desmos, let us know in the comments if this looks anything like what you got from Desmos. So the dotted diagonals. Do you want to explain those again? They're kind of your construction lines, or
yeah. So what's happening here is so sine 1 over x is always going to be bouncing between sort of -1 and 1, going like that. So on these lines, so every time sine x hits 1, it's going to hit the line y equals x, and every time it hits -1, it's going to hit y equals minus x. So the curve's always going to be bounded sort of above and below, and it's going to be bouncing between them, which is just quite useful in drawing anything that's like x cos of x, or like x or something to do trigonometric functions that'll oscillate.
Yeah, okay. So they're kind of bounds on the function that you. It's sort of a nice starting point, I guess, that you had these kind of bounds on how sine behaves. To put it in between. This function is actually used in a lot of kind of theoretical maths courses that I've seen, where people are interested in that kind of infinite frequency thing that Deepak mentioned. As you go in towards 0, it gets faster and faster oscillations as you go in, which has some strange properties. In terms of, if you're interested in things like what a derivative is, or interested in functions in general, then this is quite a strange one. And having a strange function around is pretty handy if you're trying to think about functions to do with functions in general. Right, cool. I called some people out on chat. Look, people have been called out. Very close on, very close. They're saying that it maybe approaches the asymptote from the other side.
Oh my, yeah, it does. It does.
Could do.
It
does. Yeah, I guess the way you'd work that out would be, I think maybe the best way to work it out would maybe be to go back to this statement. If a is small, sine a is about a. And then there's a fact you learn, I think at some point in year 13, that the next correction is like -1 over 6a cubed. That was a little negative thing as the correction. So I guess maybe we could have guessed that it was below. If we used all of the year 13 maths, maybe we could have guessed that it was a little bit below that. Okay, right, cool. Yeah, okay. Oh, and symmetrical in the y-axis. Yes. I think someone said it was an even function a while ago, and we didn't talk about that at all. We didn't draw anything for negative x, and maybe we could. Yeah, I guess when x is negative, I think it turns out to have a nice reflectional symmetry. So I'm going to try and draw the other half. My chance to get this right now on the left. Okay, right. I've done a terrible job, but what were we expecting? It's me drawing things. Cool, right, okay. So somehow the way the left-hand side has this infinite frequency thing going on at the origin, it's even weirder. It kind of goes in on one side, does some really weird things in the middle, and then comes out the other side again like nothing happened. Yeah, it's a little bit like, okay, somebody's mentioned bouncing balls, which reminds me to do the bouncing ball segment at some point. I've got a thing prepared on bouncing balls that's going to be in the live stream at some point. Brilliant, look, that physics, but okay, right, good. Okay, I love this. We got a set list of these, which maybe speed up slightly. Should we do elliptic curves next? What do you think?
Yeah, we can do elliptic curve.
Let's do an elliptic curve. Yeah, I think they're ready for elliptic curves. Cool. I'm going down underneath, I guess. Put an elliptic curve on screen. So this is an elliptic curve. It says y squared equals x cubed minus 2x plus 2. Cool, okay. What are we going to do for this one?
Right, so the first thing is, another good thing to look out for when sketching graphs is always symmetry. So what we can do here is rewrite this as, this is the same as y equals plus or minus the root of x cubed minus 2x plus 2. So anytime we have any solution for x, what we can just do is flip it, sort of reflect it in the x-axis. So anything that's sort of on top here, will also be reflected here, which makes our life a bit easier, because all we have to really consider is just the top, which isn't too bad. And then there's also something to just watch out for in general, which really makes drawing these elliptic curves, you get quite a variety of interesting curves, is this cubic function here. There's no guarantee really of what this does. Like, you can get cubic functions that will be, for parts of it, it'll be underneath, and for these parts where it's underneath, well, you're going to have y squared equals something negative, which is just not going to, it's literally going to be like a sort of a gap in the thing. So what you have to do is make sure you're leaving gaps at any parts where this sort of cubic becomes negative, and then you can have all sorts of weird things. So the first thing we should probably look at is, what does this cubic actually look like? And I'll be honest, I can't even remember when I gave James this. But
I realised as I dragged it onto the screen that I should have thought about the cubic before we went live. But here we are. We're live. We're going to sketch a cubic. What could go wrong? So it's x cubed minus 2x plus 2.
All right, I'll be honest. I'll say we're only really interested in the roots. I'm just thinking, does this have nice roots? I have a feeling it doesn't.
Well, I should maybe have vetted your choice of cubic then. Okay. Let's try and think about...
Factorize this cubic in the chat.
I'm going to employ some minor bits of A-level differentiation to try and find the turning points. Somebody in chat is saying implicit differentiation.
I felt like I would have given this with a decent factorization, but oh well.
I don't think you did.
Apparently not.
So this cubic on the right, it's got derivative 3x squared minus 2, which is 0 when x is plus or minus root 2 over 3. I'm aware that this is complete wizardry for people who haven't seen differentiation yet, but if you haven't seen differentiation yet, let's roll over you. I'm trying to work out where the turning points, where the kind of bits where it turns around are on the cubic. This is a technique you learn at some point in A-level. If you're year 11s, don't tune out now. It's going to come up at some point. Desmos will do it. Yeah, we could switch to Desmos, but I'm feeling too proud to switch to Desmos. Brilliant. What could possibly go wrong? So we've got 2/3 minus 2 times square root of 2 over 3 plus 2. Looks positive to looks kind of negative to me, because that's minus 4/3 root 2 over 3 plus 2. Root 2 over 3 is less than 1, so this is actually positive. I think this has got a turning point at positive root 2 over 3, but with positive value. I think it's a cubic like this. Is that good enough? Yeah, okay. That corresponds with what Molly says in chat, that it's got a negative root and then 2 complex roots.
Right, cool.
Right, there's your cubic. You're welcome.
Yeah, I think that corresponds with what graph I was aiming to sketch. So what we can see here is I've lost the mirror board.
Oh, sorry.
Right, so we have here a bit where it's negative. So as soon as it's sort of past anywhere past here, we're not really interested, because it's going to be negative. Square root of negative, it's straight up not going to exist. So if we draw, right, we're not going to be able to put any sort of actual coordinates on this without ending up solving this cubic a bit, which isn't going to be great. But what we can see is that here, so as x gets really big here, even in this cubic, am I off center?
No, it's me, don't worry, it's me. Thanks, Max.
So as x gets really big here in the cubic function, y gets also really big. So when we end up square rooting something that gets really big, it also ends up really big. So what that basically says is, as x tends towards infinity, this is also going to tend towards infinity. And then now we should so wait, is there some of them that don't know differentiation?
Yeah, but it's fine. We just did some differentiation. I feel like I might have got away with it.
Right, we can just cheat, and we can say the derivative is going to give us y dash is equal to x cubed minus 2x plus 2. Oh no, it's not, is it?
You're trying to do the implicit differentiation. Okay. Yeah.
Yeah, and this will be over 2y.
Over 2y. Ooh. I'd have written y myself, but okay, good. Yeah, go.
So what this tells us is that there's going to be 2 turning points at x equals plus or minus root 2 over 3. So bad. So we know already it's going to be blasting off to infinity somewhere. So we'll leave that as a little indication. And we know there's going to be some turning point around here. Bearing in mind that at this point it's always going to be positive anyway, so we don't really have to bother with anything because we're going to be reflecting in here anyway, right? And then there's also going to be another turning point somewhere over here, but we don't really know. And then the question really becomes, what's happening between these turning points here? Because on one hand, this just sort of blasts off to infinity, so this isn't too interesting. I think this should really be like this, to be fair, if I'm remembering the graph. I really realised I should have looked at these graphs before, but
it's more honest that we haven't, right? People will think that it's because we don't prepare these, but actually it's honesty. I've got an alternative, by the way, for people in Year 11 that's got like 2 thumbs ups. So there's a couple of Year 11s watching live, and maybe some more watching on the replay. Alternative to all this differentiation we're doing is try and sketch the cubic on the right hand side using anything by plotting values or something, which if you check some values it turns out to look a bit like this cubic. And then to get the y values we need the square root of this. So we're doing a lot of work to try and get some key features in the right place, which is a lot of work, but it's work that we know how to do because we know some bonus differentiation facts. But really we just need to work out, I can reckon I might have a go at this one just by working out square roots of things, right? So like over here, the cubic on the right hand side is 0. I know what the square root of 0 is. Square root of 0 is 0. I'm putting this point on your final graph view. At 0, the value of the cubic is 2. So on this final graph, I wanted this plus or minus the square root of 2. So I kind of got 2 points here. I guess in between I should like join the dots or something, right? I've done the left bit of your graph view. Yeah.
Oh, yeah.
So if you're not keen on differentiation, or if you just haven't seen it yet, then we can do some stuff here by sort of just checking the square roots of things. Cool. My plot's not.
So I think someone mentioned it in the chat. Well, we basically have all the pieces we need because at 0, this derivative is -2, which tells us the graph's going to be sort of sloping down a bit like this. So we basically butchered this turning point. So this is going to be sort of coming down here.
Yeah, I'm revising my left-hand sketch to have a turning point. You've convinced me that there's a turning point and it's coming down. There we go. That looks better. Okay.
Right, and then this is going to be coming blasting up, right, coming in, and then we know this is going to be a turning point. I have a feeling this turning point is secretly that turning point.
Yep.
But, so this blasts off, and there'll be a turning point here where it sort of connects with this middle bit here.
Ah, brilliant! Look at this. Here we go. And do the symmetry. Do the symmetry.
I'm trying to keep it really working.
Oh. So the square roots of this shape at the top end up looking quite similar to the same shape. It goes up, it comes down again, it goes up again. That's what the square roots of those things go up, they come down, they go up again. And we end up with this nice curve that comes round and joins around at the bottom bit over here as well. Cool. Brilliant. There's a turning point. Yeah, someone in chat has told me that the turning point is on the left. Left of 0, which you did lots of work for. And if my cubic sketch was a bit better, then I might have spotted it. Hang on, I'm just shifting it left a bit. There we go. This turning point, I knew that because it's at -√2/3. Ah, bother. Okay, right. We were aiming at one point to find the derivative of the cubic on the right, and then up here. And then a bit later we tried to find the derivative of the final graph, which is a bit more complicated because we've got this. I mean, you can think of it as having this square root in there, makes finding the derivative a bit more complicated. You did not have to do the implicit differentiation, says someone in chat, which I'm starting to think might have been true.
Oh no, yeah, you don't actually, but
cool, right, okay. And elliptic curves, what are they good for?
Elliptic curves. We're going to be a bit hand wavy because it turns out it's very complicated, but secretly you can use them for cryptography, sort of make things where you'd need a key to access something. The only way of finding that key has been given it. The only other way of solving a problem, something to do with elliptic curves, can't really tell you, is to essentially just raw power it. So someone's asking what year I'm in. I'm in first year. As you can see, me tanking the maths a bit.
We haven't taught you any elliptic curve theory yet in first year. I guess I should say.
Yeah, you did not. I feel like I'm getting torn in the chat
So-
for doing implicit differentiation.
It's like 50% people tearing into you for how you've done the implicit differentiation, which is harsh. I think you've done it fine. And then 50% like, why are you doing implicit differentiation, mate? Which is also...
Right,
Okay.
so, but yeah.
Chat, be
It's
nice.
just a
Be
cryptology.
nice.
We'll just leave it there for now.
It looks like Lulworth Cove. That's the sort of friendly comment that I like to see in chat. Brill, right.
Should we try
so-
one more graph? Should we try one graph I'm actually confident with?
Yeah, do you
Or
want to
we're
skip
gonna
to your
have time.
favourite one?
My favourite graph.
Favourite graph? Go
My
on.
favourite graph.
Yeah, okay. I've lost the set list. It's this one, right? The one I'm making
Yeah.
now. Yeah. Okay.
Alright, hopefully,
It's
hopefully I don't
quite
get
scary.
told.
You might have to justify this being your favourite graph in a moment, I'll warn you.
Oh, don't worry.
Okay. Let's try and centre this nicely. Okay. So this is x to the 2/3 plus y to the 2/3 equals a to the 2/3. What's going on here?
Just set it to 1, make our lives a bit easier.
Yeah, let's set a equals to 1.
Yeah, a equals 1. You know, none of this. Simple. Right, and then yeah. So sketching this is quite a weird curve because in some ways it sort of looks like a weird circle, but not actually. Because what you sort of have here is the x to the 3rd squared plus y to the 3rd equals 1, which is kind of like a circle. But one thing that's immediate is that there's quite a bit of symmetry. So, for example, minus x, if you plugged in minus x here, you get the exact same graph, which just tells you that if you flip it in the y-axis, it's going to be the same thing. So we have left and right symmetry. And similarly, if we plug minus y in there, you're going to get the same equation, which tells you that there's going to be symmetry in the x-axis, so it's the same flip up and down. And then also, this one isn't too well known, but here, if you sort of flip, if you imagine ripping out the x and putting in a y, and ripping out the y and putting out an x, you get the same equation. And what that corresponds to is there's symmetry in the line y equals x. So if you sort of get everything here reflected there, and everything here reflected there, so that's swapping y and x here, and you get the same equation, which tells us that it's also symmetric in this line here. So we've got quite a bit of symmetry, so we don't actually have to really sketch that much. Like, we could probably get away with sketching 1/8 of the function, and then you could reflect it everywhere else. So we'll just bother with the first quadrant now. Right. I feel like James looking a bit worried. I feel like he's just checking that my comment was right about symmetry now.
No. I love the symmetry. I've just forgotten the word quadrant. You surprised me. Good. Carry on. Sorry. Carry on.
Right, and then we can, we'll put some nice sort of points in right now. So we imagine x is 0, then y is going to be 1. Here, and similarly, if y is 0, x is going to be 1. And we know there's going to be something connecting it here, and it's also going to be symmetric in this line, and then we can just reflect this in all these 4. And now the question becomes, what's really going on here? Now, this is a bit of a shame, because I wanted to use implicit differentiation, but people really didn't like that. We can differentiate the long way, to be fair. So, wait, do the people know differentiation?
Not really.
Really.
I think when we differentiate things, I think some of the audience who have seen differentiation already know what's going on, and if you haven't seen differentiation, then doing differentiation looks completely strange. How far do you think we can get without differentiating stuff? I don't know. It's sort of a challenge mode now, right? Like if we plug in some numbers.
It is possible. It is a little bit. Oh, no, we can get there. All right. So if we consider when x equals y, so we'll just place this with like a x squiggly. So it's going to be x to the 1/3 squared plus x squiggly to the 1/3 squared equals 1, and then that'll get us x to the 2/3 equals 1/2, and this will get us x squiggly is going to be 2 to the minus 1 to the power 3/2, which is going to be 2 to the power minus 3/2. Right, and so that just gives us some point here. Right, and now what we're going to do is we're going to use the symmetry of this function. We're going to consider if we move a little bit in this x direction, what happens? Now this is squared, so this term is always going to increase. Right. And since this is always going to actually equal this one constant, this, I'm not sure I'm using a lot of arrows, this is going to have to sort of decrease to compensate. Right.
Okay. So you found this point, hang on, so you found this point on when, if you're on the line y equals x, no, I'm just recapping, sorry. If you're on the line y equals x, then you've plugged in y equals x into this equation and found the kind of intersection with that line y equals x. So x squiggly, yeah, I saw that question coming. So x squiggly was supposed to be if y equals x, and you're at the point x squiggly.
Oh yeah, it's not some complicated notation. It's not like
x squiggly is something we teach our students to use at university as a variable sometimes. Could have used a different letter like a, but we've gone for x squiggly. So if y equals x, maybe look for a point like this on the curve. X squiggly to the 1/3 squared, x squiggly to the 1/3 squared. And you found that point. And now I'm making you do this kind of complicated argument about how as you change x and you change y, what happens to points on the curve. But chat is overruling me because chat are saying that they're pretty happy with differentiation. They want to see you do it. Do you want to do the implicit differentiation? If you do the implicit differentiation, I'll try and explain what's going on.
Right.
Might be fun.
Right, we can go through implicit differentiation. So we can write this as x to the power 2/3. I'm making sure that's on. Plus y to the power 2/3 equals 1. And now what I'm going to do is I'm going to differentiate both sides with respect to x, which is sort of what implicit differentiation is all about. This might look a bit strange, but just bear with me. So firstly, we'll differentiate this term, which is going to give us 2/3 x to the minus 1/3. And then this, what you have to remember is y is just some function of x. In fact, no, I might make it a bit more complicated. So what we can do is we can just sort of... So if you imagine that when you're differentiating x, you're sort of doing the chain rule without actually realizing it. So you're you're differentiating this term, but at the end, you're multiplying it by the derivative of x with respect to x, right? So what you can do here is differentiate this the same way. So this will be 2/3 y to the minus 1/3, but then we're going to times by the derivative of the function y. But this is just dy by dx. And then, where have we gone? And then that's just 0. Because secretly, this term is also there, but d by dx of just x is just 1.
So if you've seen, let's do a little breakdown because I said I would. If you've seen some differentiation before and you've seen things like dy by dx, then you're quite set up, I guess, to be able to differentiate things like y equals some stuff. You've seen things like that before, like y equals stuff. Maybe you've seen how to differentiate those. The only thing that's different here is Deepak is using differentiation as an operation that you do to other objects, not just y equals stuff. That involves differentiating each side of the equation, so it's a little bit different. There's a kind of implicit expression here for y. It would be explicit if it just said y equals some stuff. It's implicit here because y is kind of contained within it. And the rule for differentiating it is whenever you see an x, just do what you normally do when you differentiate. So this differentiating x to the 2/3 to get 2/3 x to the minus 1/3 is something that you would get from differentiating x to the 2/3 normally. Whenever you see a y, first differentiate the function of y with respect to y, I guess, but then multiply by dy by dx. And Deepak mentioned that is the chain rule. But
I realised they don't know the chain rule. This is why I was a bit scared to go for it.
Yeah, people wanted to see this. Shouldn't x squiggly equal 1, not 2? I think x squiggly is something like 2 to the minus 3/2. That point, it turns out to be a point where it intersects the line y equals x. Cool, right, okay. This gives you some expression for dy by dx. I'm going to try and mute that thing that's going ping.
When does this end? I feel like I should be hurrying up a bit.
We got until past.
Oh, all right, I'll hurry up. So what we can do is we can rearrange this, and then this will give us dy by dx equals this is going to be minus x over y all to the power 1/3. And what this basically tells us is the gradient at the point xy, which might seem a bit strange, but if we go back up to the picture, so at this point here, x is going to be equal to 1 and y is going to be equal to 0. So as we get close to that point, noting that we're coming in from above here, what that's essentially telling us is that y is going to be getting, x is going to be getting closer and closer to 1, and y is going to be getting closer and closer to 0. So this is going to, well, I feel like I've rearranged this wrong. This is giving me, have I rearranged this right?
I think you're good. I think you're good.
Oh, these are power of minus 1/3, isn't it? This should be
yeah.
Yeah, you saw nothing. This should be minus y over x to the power of 1/3. And now, as we get to this point where y is 0, so as we get closer to this, the gradient is going to approach 0. So this slant, so if you imagine gradient, so this line, gradient of 1, gradient getting much bigger, and gradient approaching 1 will sort of look like it's flattening out. So what will happen here in this graph is this is going to start flattening out here, and we know it touches this point. And similarly, as x approaches 0 and y approaches 1, this is going to approach the gradient of, this is going to start to approach infinity. So it's going to get steeper and steeper and steeper, and it's going to end up looking like that. And then if we remember the symmetry, this is just going to be reflected, and we get a sort of weird sort of circular. These should be more curved. This should be, but I'm not going to redraw it out. So this is called an asteroid. Yeah, see, people calling me out on my mistakes. I really should have practiced a bit more for this.
The delay means that you have time to make a mistake, fix it, but still get called out in chat. Yeah, we missed a minus sign somewhere in rearranging this. So this was the idea was that having done the implicit differentiation, which maybe you've seen before, maybe you've never seen before, we end up with this thing like y over x to 1/3. Y over x to the 1/3 is really interesting. When x gets small, this gets really big, which is what we can see here. This bit is kind of sharp and pointy. I'm going to do a little zoom in bubble. This bit here is kind of sharp and pointy. When x is getting close to 0, this thing goes up really large. And when y is getting close to 0, this thing is getting close to 0 derivative. So this corner kind of looks like this kind of sharp point like this. It's kind of interesting. Somebody in the comments asked, would you do this as an interview question? And I think I probably wouldn't do this as an interview question because it's quite tough. If I did it as an interview question, then I would give people lots of help with it along the way. Great. Okay.
Right. So
you said this was your favourite graph.
This is my favourite. I'm going to tell you why this is my favourite graph. Right. It turns out where to find this graph. This ends up. This is going to be a bit. I don't think people won't have heard of some of these things here, but you're going to have to just sort of roll with it. So if you draw this, I just realised, right, so if you draw this in the complex plane, so instead of taking y, you sort of take this as I, right, and then this is x. Just work with it for now. So what we can basically say is, there's this thing called group theory, right, and it basically associates certain operations on certain groups. Right, so one group that exists is called a set of unitary matrices with determinant ones. Just ignore that. Basically, it's a square with numbers in. So if we draw a square with certain numbers in like this, right, and then if we also there's a way of multiplying these squares. If we get this square and we flip this and we found the conjugate, don't ask what the conjugate is, of all the things, and we multiplied it, and if that is 1, or the identity matrix, just bear with me, I know none of this makes much sense at all.
That's fine.
Right, if we represent it like this, it turns out, and there's another thing called the determinant of these is 1, but don't really worry about it. It turns out if we add all of these terms in these diagonals of every single possible matrix like that, it gives us the set of all points inside of here in the complex plane, right? Which is it's gonna sound absolutely barbaric, but you're just gonna have to believe it. And it turns out if you end up doing this with bigger matrices, so ones that have 9 terms in it, like this, and then you impose these same conditions, these diagonals now give you the set of points that are sort of the next. Oh.
Are you down here? Yeah, you're down here. I found you.
And then the next one is sort of, these are called hypocycloids. I'll show you how they're drawn, they're quite cool. So this is going to now, instead of being 4, oh, this is an absolutely shocking drawing.
I kind of get the point. You're trying to draw like a 5-pointed star with...
Yeah, so it's essentially...
It's mad.
Right, yes. You'll see this in the GIF. You'll see what I mean.
Let me know when you want the GIF on screen.
Yeah, but the way these are drawn are you take in the plane. I might have to draw this a bit big. You might have to pan around, James.
Yep. So
if you take all this and then you draw a gigantic circle, right? Oh mate, imagine that centered.
It's fine.
You have to bear with him. I'm a bit bad at drawing on these tablets. And then if you imagine it, you bring a circle like this, that's 1/4 the radius, right? And then you attach a length of rod here, and you stick a pen. This is a bit like them things that you give kids. You know that you spin round and it draws certain patterns.
With the 2 cogs, right? Like the small cog and the big outside cog. Yeah. Okay.
You end up pushing it this way. You're gonna get the circle would have moved, but as this moves, this is going to have traced some path that looks a little bit like this. So if you end up continuing this along the way, you'll get all sorts of shapes. And the shape that we've drawn here, the asteroid, this is just a case where the ratio radius is, I think, this is 1/4. Right. And it turns out you can get the set of all the points that are inside of these by doing this weird matrix thing that I'm on about. And then if you do even more group theory, I'm not going to bother. I had stuff written down to prove, but I realised it's not going to happen. And then it basically turns out that you can prove that the set of points inside of this is sort of the exact same thing. Oh, see, this is really going to be tested my drawing skills. So if we imagine a 5-pointed star, and then we imagine an asteroid sort of centered like that. If we rotate this one, if we do the exact same thing with any point on here, as we rotate it this way round, every point in this will end up tracing out this entire shape here. But the way to prove that is secretly some like weird matrix stuff that just, yeah, spirograph, is that, I don't know, is that like what they're called? But but I think James has got a GIF to show you what I mean if I've absolutely butchered the explanation.
No, I'm going. So you want the GIF now, yeah?
I want the GIF. I feel like
we coordinated this bit. Deepak has sent me this GIF that I can put on screen. Oh, hello. I need to switch to the bit where you can see it. I love, by the way, that I asked the mathematician, why is this your favourite graph? And the answer went, complex numbers, matrix theory, put them in the Argand diagram, and then you know those kind of rotating circles inside other circles, but then you rotate those inside the other ones, and it's why I love talking about maths with people, is that people love finding connections between things. So on screen, I can see.
Graph, you can sort of see it sort of looks like a square. You can see the asteroid in that rotating inside, sort of tracing out the one that's the 5-pointed star up, and each of them will fit perfectly in each of the rest of the ones. And then there's a degenerate case there where it's just a line which works. But
so these different colours are different asteroids, you said. Let's finish on this point, I suppose. These colours are different asteroids. They're what you get when you roll a circle around the inside of a larger circle. So you've got a large circle and a small circle. You roll the small circle around the inside, and you trace out one point on the smaller circle. You get these asteroid shapes, and then this GIF is brilliantly rolling one of those inside one of the others around in circles. Brilliant stuff. I don't understand, but I believe you, says a parallelogram in chat, which I think sums up where we might have got to. Cool. Am I trying to hypnotise you? No. Maybe I'll turn this off now. Let's switch back to this. Brilliant stuff. I'm going to roll. We're going to put together because we're running out of time. I've seen people talking about stuff in chat below. We've been putting together some further reading for each one, and we might put some stuff on implicit differentiation and that GIF. They go on the website. There's a link to the website. I don't really know how you find the live stream without finding the website, but there's a website, maths.ox.ac.uk/r/club, which is our kind of club website. It's got all of the kind of links you need for the club. It's got previous episodes. It's got extra further reading on stuff that we talk about those. We update the website with further reading stuff every Friday. We experimented with sending it out in emails, but who even uses emails anymore? It's all websites now, and we get better maths formatting on the website. So we've switched recently to just putting it on the website for everyone. I'm lost, says someone, and that's, I think, fair. Right, cool, right.
Yeah,
rolling
that guy
shapes.
as well, he said it's the ratio's 1/n+1 for the n-pointed... they're technically called hypocycloids, but, you know.
Oh, I love this. You even had the complex numbers inside the matrices. Brilliant stuff, right.
Yeah.
I'm going to wrap up by talking to chat a bit. Oh, should we set some of these as... I had an ad break, but it doesn't really make sense to do an ad break with 5 minutes to go. I guess we've got these last two, which we can talk about, why we like them. We can talk about why we like them. Maybe we don't have time to sketch these, but we also had these on our kind of set list of functions we like. Just for 2 minutes. I guess we'll set these as kind of homework to try and sketch these yourself. They both involve exponentials. The one on the left is... Again, things multiply together. So if you liked that bit of having x multiplied by sine, there's the thing on the left to have x squared multiplied by e to the minus x squared. Have a think about what on earth that looks like. Which is quite nice. So multiplying things together again. Think about envelopes. Think about what's going on for very large x. Think about what's going on for very small x. And try to approximate things for big and small x. Might be something you could do there on the left. Just email them a tech document. Emails are surprisingly good for that. Yeah, okay, that does work a bit, I guess. And there's something on the right, which is e to the x over e to the x plus 1. Do you want to say what this function is used for? They won't believe you.
There, on the right. I'm not going to spoil what it does,
Okay.
but what it can be used in. So one of the main uses, it's actually gone out of fashion a bit nowadays, but it's using machine learning algorithms. And if you sort of imagine what they do is they get all these sort of like neurons, right, that each associate something. Say, I'm trying not to make it more confusing. And so what they end up doing is they use it to sort of, because they have all these hundreds of neurons sort of connected to different inputs and different outputs, and they get inputs from all of these neurons, and at the end, they need to associate each possible sort of outcome with a probability. Right.
So you've got.
I'm really trying not to spoil it.
No. We don't want to spoil what it looks like because they might be trying to sketch it themselves, or they might still have Desmos open from earlier. Who knows? But yeah. So the idea, I guess, your neurons in your neural net model might be on or off, and you might want some sort of control over it. You've got some input that maybe that neuron decides to turn on if it's got enough input in. And you need some sort of switching thing that decides whether it's on or off based on the input, therefore. And it's probably mysterious enough that they might go and sketch it without telling them what it looks like as an answer.
Oh, I've got a good graph. We're not going to sketch it, but I'll leave this for people who like Desmos. This is a fantastic graph. I probably wouldn't try sketching this one. This is one that's just, it's quite literally called the Devil's Curve.
Oh my word.
I'm not why, but it's good fun to mess around.
Y squared minus A equals x squared minus B, and Desmos will let you put sliders for A and B, I'm sure. Right,
was
cool.
step 3, I think, a couple of years ago, maybe like last year. So it is very tricky to sketch. So it's cool to mess around with them, Desmos.
Brilliant stuff. Thank you very much, Deepak. It's been great fun having you on the live stream. Thanks everyone for watching. I'm going to hang out in chat. Thank you to Lauren and Max, who've been managing chat all the way through. Thank you both of them. I'm going to hang out in chat for a little bit. I saw some admissions sort of questions come in. If we haven't answered your admissions question on the stream, I will jump in chat and try and answer that after we're live now. Otherwise, we will see you in 167 hours for another episode of the Oxford Online Maths Club. Bye.
Bye, guys.
I need to press the button. I always get this bit wrong. Right, okay. There.